Hello, my name is Olgaaurora Rodriguez, and I am here today to talk about biomass-derived nanofiltration membranes for drinking water purification. I conducted my research with Dr. Zhao in the chemistry department. We used mulberry leaves and silkworm waste, cheap biomasses, to create membranes that would efficiently purify hormone-contaminated water into purified water. So why is this research important? This research project is very important and interesting because it tries to find an environment-friendly and economic process in which to obtain purified water. Yes, there are currently ways to purify water, but majority are not eco-friendly or cheap. If this experiment were to obtain positive results, that is, to efficiently purify contaminated water, this process could be used in mass production to purify water and help the environment. FTIR, or Fourier spectroscopy, was used to observe the properties of the solution before and after being filtered to examine the membrane's efficiency. XRD, or X-ray diffraction, was used to observe the properties of the membrane. Now let us discuss the material and methods of this experiment. In this section right here, we see that the overall materials used were heat annealed carbonized silkworm wastes, or CSW, there was also concentrated sulfuric acid, 30% hydrogen peroxide, and distilled water. The membranes were made using 0.3 and zero point 0.1 micron filters. The millipore glass vacuum filtration system, which will be discussed later more in detail. Saturated EE2 aqueous solution, EE2 in mixed solvent, which was created from 5 grams of EE2, 1 milliliter of hydrogen peroxide, and 9 milliliters of HCl. UV-vis spectroscopy was made by using 1 mm cuvette and 1 centimeter cuvette with a UV-vis spectrophotometer. The experimental procedures were 5.87 grams of carbonized silkworm waste, doped with 0.01, 0.1, and 1% of nickel iron ions, were mixed with a 2:18 ratio of concentration sulfuric acid and 30% hydrogen peroxide for 20 minutes. 125 milliliters of distilled water were added and centrifuged for about 110 minutes at 10,000 rates per minute. The wash centrifuge cycle continued until the pH of the solution was 3.47. The silkworm centrifuge solution was used to create multiple membranes of various concentrations to study the spectroscopic properties of the filtered solutions. UV-vis absorption spectroscopic measurements were carried out on a Allegiant Carry 60 UV-vis spectrophotometer. For comparison, UV-vis visible spectra of EE2 stock solutions were measured and compared with those of EE2 filtrates for rejection rate calculations. Now here in the filtration setup section, we can observe the side view of the setup in the left image and the top view in the right image. Moving on to the results section, here we are. In figure 1, on the image to the left, we can see one of the biomasses used in the experiment, which is mulberry leaves that are consumed by silkworms. On the right, we can also see the other biomass used, which is annealed silkworm waste with nickel iron ions, doped concentrations of 0%, 0.01%, 0.1%, 1%, and 2% from left to right. Under figure 1 to the left is the hormone abbreviated as EE2, used to make the experimental contaminated water. In figure 2, we see the membranes created from the suspension of carbonized silkworm waste with a 4.1 milligram per milliliter concentration. Now I will discuss figures 3, 4, and 5 together. In figure 3, we see the absorption spectra of EE2 mixed solvent stock solution and filtrates passing through two CSW membranes in different thicknesses. In figure 4, we see absorption spectra of EE2 solutions before and after filtration of a CVS membrane. And in figure 5, we see the absorption spectra of EE2 solutions before and after filtration with a second CSW membrane. UV-vis measurements were obtained from the filter for the filtrate and that we ran through the membrane. Since Beer's law relates the concentration of a solution to be directly proportional to its absorbance, it was used to find the absorbance of the hormone EE2 by each filtrate to determine the effectiveness of the membranes. This was done by, for example, here in figure 3, by taking the peak of the blank, in this case, in this child, a mixed EE2 solvent stock solution, and that was used as the background. We did 1 minus, for example, if we wanted to find for the thin membrane, we would take 1 minus that divided by the blank, which was this as previously mentioned, and then times 100 to get the rejection rate. The rejection rate for the membrane was 19. The rejection rate for the thin membrane was 19%, and for the thick membrane was 31%, which is found in figure 3. This leads us to the conclusion that thick membranes are more effective than thin ones in purifying water. The rejection rate of EE2 filtrate in figure 4 was 87%, while the rejection rate of EE2 filtrate in figure 5 was 95%. The flow rates of the EE2 solutions discussed in figures 3 through 5 are shown in table 1. The flow rate unit was liter over hour per meter square per bar. Now in the reference section over here are the scientific articles which were referred to for this experiment. Lastly is the acknowledgements section. I would like to thank my professor, Dr. Zhao, and my colleagues Anthony and Daniel for all their help throughout the experiment. I would also like to give a special thanks to the Signature Experience Grant and UALR Cluster C grant for financially making this experiment possible. Thank you so much for being here today, and I hope you enjoyed it. Have a great day.